Lesson 3, the discriminant. In this lesson, our goal is to identify a method for determining the number of roots of a quadratic equation. Notice I said number of roots because this method doesn't actually tell you what the roots are. Here we go. Let's begin with a warm-up. In this warm-up, you're going to use the quadratic formula to find the roots of the quadratic function f of x equals 2x squared plus x plus 6. Now is a good time to pause the video to try this on your own. When you're ready, click play again to resume. Okay, here we go. Let's begin by writing out the quadratic formula, which I hope you remember is x equals negative b plus or minus the square root of b squared minus 4ac, and all of that is divided by 2 times a. Now you substitute your a, b, and c, so let's look at the quadratic function first. Don't forget that the a value is just the coefficient of the x squared term, so in this case a is 2. The b value is just the coefficient of the x term, in this case b is 1. And finally, c is just a number on its own with no x's. In this case, it would be 6. Substituting into the quadratic formula, we get the following. Negative 1 plus or minus the square root of 1 squared minus 4 multiplied by 2 multiplied by 6. And that's all over 2 times a. Let's try and simplify this without a calculator. Don't forget to use the rules of BEDMAS. So in the numerator, we've got negative 1 plus or minus. Under the square root, we're going to start simplifying. Squaring 1, we get 1. And now we subtract the product of 4, 2, and 6. 4 times 2 is 8, times 6 is 48. Don't forget to keep the negative there because you're subtracting that whole entire product. And all of that is divided by 4. Continuing to use BEDMAS, we're going to simplify what's under the square root first. So 1 minus 48 gives you negative 47. And all of that is divided by 4. And you'll see we arrive at a problem. We're trying to take the square root of a negative number. As you know, we can't do that. So this suggests to us that there are no solutions. And you may be wondering, why did we go through all of that trouble just for no solutions? The reason is we didn't know. Lucky for us though, the discriminant is a way to figure this out ahead of time without having to go through all that work. And this is exactly what the lesson is about today. Before we get into it though, let's visually look at what it means for a quadratic equation to have roots. This is shown in the picture below. Notice we have one of 3 possible options. A quadratic equation can have 2 roots. What this represents though on the graph is a parabola that crosses the x-axis twice. Here's your x-axis. I'll just highlight that to make it a little more clear. Here's your y-axis. And notice that our parabola crosses the x-axis twice. That means it has 2 x-intercepts, and in terms of the quadratic equation, it would have 2 roots. Next up, the other case is 1 root. In this case, notice that your parabola crosses the x-axis just once. And finally, 0 roots. If you look at the picture, you'll see that the parabola completely misses the x-axis. It never even crosses it. And that's actually what happened in our warm-up. When you try to find the number of solutions for a parabola that misses the x-axis, you're going to get one of these cases where you try to square root a negative number. In other words, it's not possible to find solutions. So notice the discriminant is just a way to tell us how many there are, not what they actually are. And now let's go into that in more depth. So algebraically, the discriminant is just simply an expression. And it's one that determines the value of the number inside of the square root part of the quadratic formula. Sorry, little typo there. Change that to formula, please. I really have to have a word with my editors. So here's the discriminant. It's equivalent to b squared minus 4ac. And once again, notice that's just the expression under the square root of the quadratic formula. We have one of three possibilities. The first one is if your discriminant is a positive number, in other words, greater than 0, then that tells us that there are two distinct roots. Distinct is just a word meaning different. This means that you're going to have two different x-intercepts on the graph or two different solutions when you try to solve it using the quadratic formula. The other case is that your discriminant equals 0. And in that case, there's one distinct root, meaning there's just one solution. And finally, if your discriminant is negative, then that's going to be the case where there are no roots. That's the parabola that doesn't cross the x-axis. So now that we've seen the three different cases, let's practice in an example. In example 1, you're asked to determine the number of roots. Remember, this means how many are there, not what they are, in each of the following. This would be a good time to pause the video, try it on your own, and click play when you're ready to resume. Okay, here we go. This is just three applications of the discriminant. So I'll write it out for the first one. Our discriminant is b squared minus 4ac. At this point, you just substitute. So our b value is negative 3. I'm putting brackets because it's negative. You have to square the value as is. And you're subtracting 4 times a, which is 2, multiplied by c, which is negative 5. Brackets are very important for an operation like this. I would encourage you to try this without a calculator. So negative 3 squared gives you positive 9. And you're subtracting the product of 4 times 2 times negative 5. 4 times 2 is 8. 8 times negative 5 is negative 40. Don't forget we have the negative in front still. So now we simplify this. We have 9, take away negative 40. That turns into 9 plus 40, which will simplify to give you 49. Now notice our discriminant came out positive. Once again, we didn't care what the number was, just that it's positive. So therefore, this quadratic equation has two distinct or different roots. Part B, we'll write out our discriminant once again. So that's b squared minus 4ac. B happens to be 4. And you're subtracting the product of 4 times 1. Simplifying this, we get 16, take away, 16, and that simplifies to 0. Now our discriminant is 0, so that tells us that we have one distinct root. And finally, part C, one more application of the discriminant. So here we go. Substituting again, so we have a b value of 1 this time. Our a value is negative 5, and the c value is negative 2. 1 squared is 1, and you're subtracting the product of 4 times negative 5 times negative 2. So let's see. That's going to be negative 20 times negative 2. That's going to work out to be positive 40. So you're subtracting 40. 1 minus 40 gives you negative 39. And once again, we don't care what the value is, just that it's negative. So therefore, this tells us that there are no roots. And there you have it, 3 examples of using the discriminant. Moving on now in example 2, we have a thinking question. So let's take a look. You're asked to determine the value of k such that this quadratic function f of x equals x squared, take away k times x plus 3 has one distinct root. So let's see why this is a thinking question. The reason is you don't know what k is, but you want to find it so that there's one distinct root over here. Notice the question didn't ask what the root was, just that there's one of them. So anytime a question asks you anything to do with the number of roots, it's definitely an application of the discriminant. Let's begin by writing it out. Our discriminant, remember, is b squared minus 4ac. What has to be true about the discriminant for it to have one distinct root? Well, it has to equal 0. So the left side of this expression will equal 0. And that's how we set this up, and now we can go ahead and plug in a, b, and c. So be careful here. The b value is the number in front of the k. In this case, it's not a number, it's an expression. So let's go through this one term at a time. The number in front of the x squared is 1, so that's your a value. The thing in front of the x, in this case, is negative k, so that's your b value. And finally, the number on its own is 3, so that's the c value. Plug those in as is. So 0 has to equal b squared, so that's negative k all squared. Take away 4 times 1 times 3. And let's just look at this for a moment. We have one equation with one unknown, and we should be able to solve for k now, which is exactly what we wanted to do. So let's do that. We're going to start simplifying. That's going to give you positive k squared, and you're going to subtract from that 4 times 1 times 3, which is 12. Our job now is to solve for k. Whenever you're solving for a variable, use reverse BEDMAS, or as it's commonly referred to, SAMDEB. So we'll undo subtraction and addition first. We'll bring the negative 12 over to the left side, making it positive. Now we've got to undo the square. We do that by taking the square root of both sides. Let's do that. Now don't forget, anytime you go out of your way to take a square root, you have to put the plus or minus in front because it could be either or, we don't know. And we're pretty much done. You get square root 12 on your calculator, you'll get a decimal number. But as we saw in lesson 1 of this unit, we can simplify this radical as follows. So we can break down 12 into the following. Remember, like what we did in lesson 1, whenever you're simplifying radicals, you try to write the number underneath as a product of two numbers, ideally where one of them is square rootable. So we can break up 12 into 4 times 3. We'll use a property that we learned in lesson 1. The root of a product is the product of the roots, which I'll write out right here. Okay, we can square root 4, that's going to give us exactly 2. We can't square root 3, so just leave it as root 3. And that's going to be your simplified final answer. Moving on, we have a much more complicated example here. It's very similar to what we did previously, but a little more difficult. Let's take a look. In this example, we're given the following quadratic equation. K plus 3 in brackets multiplied by x squared plus 6x plus k, and that's all equal to 5. We're told that this quadratic equation has two distinct roots, and we want to find all possible values of k to make this true. So remember, anytime a question deals with the number of roots, think the discriminant. But first, notice that this quadratic equation is not in standard form. A quadratic equation always has to equal 0. So let's make it equal to 0. To do that, we can bring the 5 over to the left side, and then we'll have it in standard form. So we have k plus 3 in brackets multiplied by x squared plus 6 times x plus k take away 5, and that all equals 0. If you were to analyze this now, let's pick out our a, b, and c. So a has to be the thing in front of the x squared. In this case, it's the expression k plus 3. The b value is just simply the number in front of the x. In this case, it's 6. And finally, the c value is always the number on its own without an x. In this case, it's also an expression, a little more complicated, but you can see that that expression has no x, so it's the leftover term, that's the c value. With that being said, we're able to set up our discriminant now. We want our discriminant to essentially be greater than 0 because that's the case that leads to two distinct roots. So what has to be true is that b squared minus 4ac has to be greater than 0. Notice this is more complicated than the previous one because before we just set it equal to 0. Now we're making this expression greater than 0. This suggests there might be more than one possible answer. As before, let's substitute. So b is 6. The a value is the expression k plus 3. Just substitute that as is. And the c value is the expression k minus 5. And all of that has to be greater than 0. Well, let's look at the left-hand side. Notice that there's only one variable, k, but the problem is it's all over the place right now, and there's really not much we can do at the moment. So what we should do, it might not seem obvious, but let's simplify this. So I'll do that. We can square 6 to get 36. Now we have to deal with the k's. Well, we're multiplying two binomials, so let's use FOIL over here. So we're going to expand the following to get k squared, take away 5 times k, plus 3 times k, take away 15, close your bracket, and all of that has to be greater than 0. Let's continue to simplify. We can distribute the negative 4 into the brackets. And then I'll collect all my like terms at the end. Alright, let's collect our like terms, and we'll also write it in proper order of descending powers, meaning we'll put the negative 4k squared first, collect like terms, 20k take away 12k gives you positive 8k, and finally 36 plus 60 gives you 96, and this simplified expression still has to be greater than 0. At this point, we're trying to find where the thing on the left side is greater than 0. It may not seem obvious, but it'll actually be beneficial if we factor this. You'll see why. We have a trinomial on the left. Let's begin factoring like we always do. Look for a greatest common factor. So we can definitely pull out a negative 4 from every single term, and that's going to simplify to give us the following. I'm just dividing everything by negative 4. Now inside the brackets you have a simple trinomial. We can factor it further, so we want to look for two numbers that multiply to negative 24 and add up to negative 2. Think for a moment what those numbers could be. And hopefully you found negative 6 and positive 4. And there we have it. We fully factored the left-hand side of this expression. Notice that on the left side, we actually have a product. We have negative 4 multiplied by k minus 6 multiplied by k plus 4. I'm going to highlight the three products here just to make it a little more clear. Now, there's something very powerful to this expression. What this expression is trying to tell us is, where is this product greater than 0? In other words, where is it a positive number? So for example, how can you get a positive number? If you were to multiply two negatives, you would get a positive. If you multiply two positives, you get a positive. So here we have negative 4 multiplied by k minus 6 multiplied by k plus 4. I'd like you to think of this whole entire thing as an equation. I know it's not equal to 0, it has to be greater than 0, but you can still think of it like an equation. So with that being said, looking at the left side, we're multiplying three things. Notice that the negative 4 is always going to be negative. What would have to be true about k minus 6 and k plus 4 in order for the product to be positive? Well, let's say that k minus 6 is a negative number. Now we have negative times negative, which gives you positive. So what would have to be true about the k plus 4? That would have to actually be a positive number. Because when you multiply a negative by a negative by a positive, you get a positive number. That's not the only possibility, though. Let's take a look at the other one. Now, notice that negative 4 once again is still negative. But what if k minus 6 was a positive number? If that was the case, then negative times positive gives you negative. So the k plus 4 would have to be negative. This is going to lead to two possibilities, or two different cases. We have to consider them both. So I'm going to do that now. Let's consider case number 1. In case number 1, we showed that the expression k minus 6 had to be negative or less than 0, and the expression k plus 4 had to be positive. I'd like you to treat each of these expressions like equations. So where is k minus 6 less than 0? For example, what if k is 1? Then 1 take away 6 is negative 5, which is definitely less than 0 or negative, so that would be true. But what if k was 7? Then 7 take away 6 is 1, which is positive. It doesn't work. The way to find the solution for all of them is to solve this just like any equation. So you can bring the negative 6 to the other side, and that's going to give you now k has to be less than but not equal to 6. And if you do the same thing for the other one, you get that k has to be greater than negative 4. We're just moving the number to the other side of the greater than sign. You treat it exactly like an equal to sign, which is why it flips signs. So for case number 1, we showed that k has to be less than 6 and greater than negative 4. Let me ask you, is it possible for a number to be both less than 6 and greater than negative 4? You can sketch a number line to help you visualize that. So negative 4 would be somewhere here. Positive 6 would be somewhere here. And notice any number that's greater than negative 4 and less than positive 6 is going to be somewhere in between the two. So basically all numbers between negative 4 and 6, not including either, are going to give you a solution. That's case number 1. We now have to consider case number 2. So I'll do that up here somewhere. Let's see. Let's do case number 2. So here, we said that k minus 6 had to be positive, and k plus 4 has to be negative. So just like we did before, let's solve each of these separately. That's going to lead to two solutions. One of them is that k has to be greater than positive 6, and k has to be less than negative 4. In a similar way, let me ask you, is it possible for a number to be both greater than 6 and less than negative 4? Let's look at the number line. So all numbers that are greater than 6 are somewhere to the right here. All numbers that are less than negative 4 are somewhere to the left here. Notice that it's not possible to be both greater than 6 and less than negative 4. So we actually get no possible solutions for case 2. Therefore, the only case that led to solutions was case 1, and we can summarize that in a therefore statement. So therefore, the quadratic equation has 2 roots whenever k is between -4 and 6. And to summarize this, we're going to write an expression that kind of looks like a sandwich, just like we did with domain and range. We read this left to right by saying -4 is less than k, which is less than +6. And let's test this. So what's the number between -4 and 6? For example, 0. I want you to look back to the expression right over here that I'm starring, the one where I highlighted it. If you plug in 0 for k, is the expression greater than 0? Let's try it out. 0 take away 6 is -6. 0 plus 4 is 4. Multiplying -4 by -6 gives you 24. By +4 gives you 96, which is definitely greater than 0. Feel free to try it out for other numbers between -4 and +6. You can even try it for decimals, like maybe 3.1, for example. As long as you aren't equal to -4 or equal to 6, it will work. So that was a tough one, and that's probably as hard as examples are going to get in this unit. Feel free to rewind it if you need to take a look again. And with that being said, we'll move on to our very last example of the lesson, which is a word problem. So in example 4, we're being given an example related to business here. We're told that the profit of a business is represented by this equation. P of x, which is equal to R of x minus C of x. We're told that R of x is the revenue function and C of x is the cost function. So just to remind you, revenue is the money that a business brings in, but that's not the money they keep because businesses have costs associated with them. For example, they have to pay their rent, pay their staff, pay their hydro bills, etc. When you subtract revenue and cost, whatever is left over is your profit, and if you're a business, you definitely want your profit to be a positive number. So with that being said, in this example, we're told that x represents the number of coffee cups that a coffee shop sells. We're given expressions for the revenue and for the cost functions, and we want to determine an expression for the profit. So feel free to try this on your own, pause the video, and click play again when you're ready to resume. Here we go. So our profit function, remember, is the revenue function minus the cost function. At this point, you can just substitute for both revenue and cost. So the revenue function is -2x squared plus 6 times x. And the cost function, I'm going to put brackets here because you have to subtract all of it, is -x squared plus 4x take away 5. And now we'll just simplify by collecting like terms, just like we did way back in Unit 1. So we've got -2x squared plus 6x. Distributing the negative now into the brackets, you get +x squared take away 4x plus 5. And at this point, you just collect your like terms. So we add up the x squared to get -x squared. Add up the x's to get +2x. And you have just the 5 on its own. And there you go. That's going to be a simplified expression that represents the profit in this example. In part B, we're asked how many roots does it have. So once again, not what they are, but how many they are. Anytime a question asks you how many there are, you have to use the discriminant. So let's write it out. Our discriminant, remember, is b squared minus 4ac. And I'll just scroll up a bit to see the function from the previous example. We have a b value of 2, that's the number in front of the x. We have an A value of -1 and a C value of 5. So we just go ahead and simplify. Let's see, that's going to give us 4. Take away the product of 4 times -1 times 5, which is going to simplify to give you -20. But you're subtracting -20, so that's going to be 4 plus 20, which gives you positive 24 as your final answer. What can we conclude from this? Our discriminant is positive, so therefore the profit function has two distinct roots. And finally, what do the roots of the profit function represent? So you got to think a little bit about what we're representing here. So the roots of any function are here, let's write this out. So the roots of any function represent where the function equals 0. In this case, where our profit function p of x equals 0. Think about what you just wrote. You're trying to find where the profit function equals 0. So what the roots represent, let's go back a bit though. We're dealing with x, and our variable x, we were told, is the number of cups of coffee. So the roots represent the number of cups of coffee that you sell such that your profit is 0. Let's write that down. In business, we call those the break-even points. So the roots represent the break-even points. When a business breaks even, its revenue equals its costs and it's not making any profit. This isn't always a bad thing for a business, but certainly businesses want to be profitable and therefore have a positive profit. Okay, that's going to wrap up lesson 3. You have some recommended homework here from the textbook. Feel free to try as much of it as you can, and that'll wrap it up. Take care.